Welcome to this little video lecture about data structures in the memory of a running Haskell program, how they look like, how ghc manages the heap, and how you can see things like sharing, laziness, and memoization in the running memory of a running Haskell program. And we will use a fancialized tool for that called ghc-vis, written by Dennis Felsing, that allows us to inspect the memory of a running program in a nicely graphical way. So first we have to install it. Installation of that tool is sometimes a bit annoying. On the one hand, it kind of depends on the precise version of ghc that you're using. So if with the very newest ghc, you might have problems installing it. On the other hand, it uses GTK and svg-cairo and libraries like this that bind to C libraries to visualize things. So you need to have the C libraries installed. That depends on how on your Linux system. And then also the Haskell bindings sometimes are tricky to compile. So what I usually do is I go to an empty directory and I install it using cabal. And using this --env dot flag, I'm basically registering this library in just the current directory. Nothing else, no project file needed. And then I can use thdi in this directory and the package is there. If I do this right now, it'll complain that svg-cairo doesn't work with the version of cabal that I have using here, but I can tell cabal to ignore that, and actually it works. So this will be now relatively fast because it's already compiled in my cabal cache. So this is the setup we need. Now I can run ghci and it tells me, yes, I've loaded something from a package environment file in the local directory, and I can import ghc-vis now. This gives me a few commands I can run in ghci. The first one that we need is vis, which opens a new window. So this is now two windows. I'm using a tiling window manager here. And then I can start to inspect certain values using view. So for that I say view and then I pass some value, maybe just one, and I also give it a name. Something like this. And now I get this graphical view here. And what we see here is really a very honest representation or visualization of what's happening in the memory of my running Haskell program. So the value that we've just labeled as just one, that is an object on the heap, object in the sense of structured thing. It's 2 boxes wide. So here we have 2 boxes in this visualization, so it's 2 words in size. And on this machine, 64 bits, every word is 8 bytes. So this is actually 16 bytes. The first one, which is just represented here as just, is actually a pointer to something called an info table that has various information for the runtime, like how big is this object, where are pointers in the object, where is data in the object, and so on. And then the second element, the second word of this data structure is itself a pointer, which is represented here as an arrow, to another heap object, in this case a integer, namely the integer 1. The integer itself is not directly in the just. There is a separate object on the heap, and the just constructor just contains a pointer to that object. And that other object is also 2 words in size, also 16 bytes. And the tag here, the constructor, the info table says this is a small integer. And then we actually have the value right there in the constructor. So this is no longer a pointer, this is really just the value 1 as one word. The s hash, that's one of the 2 constructors that ghc uses to represent integers, the unbounded data type. The other one would be j hash for really large ones. And if we compare that with what we get if we explicitly say that this one should be an int, then we see that they look rather similar, but they are this int type, which is always machine word size. It's still a boxed thing. It's still something that has 2 words on memory and is pointed to, but it has a different constructor, the I hash, and you will see that a few times later. and then the number 1. We can also look at the nothing value. So nothing, that would be a constructor without any arguments. And we see that in the memory, this actually looks like it has some argument. It's still 2 words. And this is an artifact of an implementation choice in GHC, namely that all objects on the heap are at least 2 words in size. And the reason for that is that the garbage collector needs some space to move things around. And even though this is a static value that usually doesn't get touched by the garbage collector, there's something about compact regions where then this still needs to be the case. So for our purposes, this means that values like nothing or also the empty list, they have this odd number as part of their data structure, and we just ignore that. Of course, we can also nest these constructors. So if I would say just of one of int, and let's maybe call that jj1, jji, then, well, you get what you expect. There's a constructor just, and it points to another constructor just, and that points to the number 1. It's maybe interesting to notice that there's only one number 1 here, so both of the cases of just 1 that we have here share that value. And that is optimization that GHG applies specifically to small numbers and also small characters. That's why we'll see it later. But also note that we have 2 constructors that are semantically the same thing. In both cases, it's just 1, but there are 2 separate objects in the memory. So it's not the case that every time you recreate the same value, if it's already there, it'll be reused, but rather you will be recreating it. And this is good to know. Okay, we've now seen how to read these visualizations. Let's look at more interesting data structures. In particular, let's look at lists. With the command clear, I can clear the view, and I can start with the new definitions now. A good way to create a list is to say, to use strings, because strings are just list of characters. So here's a list hello, and I can look at this, and I now see that lists consist of either the cons constructor, the colon, which contains the first element of that list and then the tail of that list, the continuation of the list. And that continuation can either be another constructor, also called cons, or it can be, at the end, the empty list, the nil. You can also see here that GHC has reused the same object on the heap for the L. And this is what I said, this is optimization, where small numbers, small specific characters, they're basically there once. And as soon as the garbage collector sees another one of these, it just takes the static one, the pre-allocated one. This can be confusing in these views, so I will not work with the word hello, but rather with the word uncopyrightable, which is one of the longest English words without duplicated letters. So here we really see that strings and therefore lists in general are just linked lists. So we have one element, there's the U, and then a pointer to the next element of the list where we store the N and then the C and so on. And you can also tell from this visualization that there's a nice name for the sequence of constructors that goes down from the beginning to the tail, to the nil. It's sometimes called the spine of the list. You might encounter that if you read about spine-strict functions and so on. And in this visualization, it's quite nice to see that why this is a spine. This looks like the spine of a very scary animal. All right, let's do something with that list. There are 2 operations we can do on lists that you probably know. There's take and there's drop, which take the first prefix of a list or give you the suffix of a list. So let's define L2 as taking the first 5 elements of the list, and L3 as dropping 5 elements of that list. So L2 becomes uncop, and L3 becomes writable. Very similar dual functions, but when you actually look at what they do to the memory of your program, what their effect is on the heap, they're actually quite different. So the L2, the initial prefix of that list, that is actually a copy of the list. So L2 in order to return that prefix, the code had to allocate new constructors for the 5 elements in that list. It is still sharing the element. So that's why the L2 has a separate list constructor than L, but they're both pointing to the same element as the first element of the list. And this is not just because of this optimization that I mentioned for small characters. We would see this kind of sharing also if there were more complicated values in the list. Now let's compare that to L3, the function that we got as a result of using drop. And L3 is actually just this thing here. And notice that it's pointing to this a part of the original list. So if we follow the pointers from L, then we see that this is just the spine of L, which after the 5th element points to this cons cell, this constructor, and L3 is just that. It kind of makes sense that as you're dropping elements from a list, you're basically just passing through the list until you have passed enough elements, and whatever is then left of the list, that is the tail of the list, or in this case the dropped list, and you can just reuse that data structure in the memory. But of course, this kind of reuse, this kind of sharing, which is maybe the more common term, only works because Haskell is a pure language, where you can't just mutate values, because otherwise you would now have L in L2, and you might be tempted to go into L2 and then change some value there, and it would suddenly affect it. And this kind of effect as a distance, that is what makes imperative programming hard, and working with pure functional programming is so much nicer. Oh, one of the many reasons, I guess. So this is sharing. I also promised to look a little bit into laziness. And for that, let's clear the view again. Let's look at L. So we'll still start with our first list L. And now let's apply a function over it that happens to be lazy. And one obvious one that we can use is map. So let's define L2 as map data jar to upper of L. And to upper needs to have an uppercase U. If I now view L2 here, we get something ugly. So this will always happen, or almost always, when you just use ghgi to look at these values. And really this is just basically the first, like the constructing the initial computation, so to say. And really once we look at the first bit of that value, that will go away. So let's just look at L2, but just at the head. We don't want to evaluate too much of it. No? And then we can update the view. So the update command just refreshes the view, and now we have something a bit more easy to look at. And we see that L2 is also a list, where it starts as any other list we've seen so far. The first element is the capital U, that makes sense. And then the tail of that list, the continuation, is a thunk. The thunk is an expression for, or is a term we use for an unevaluated expression. This is not yet a value. We don't know yet whether this is going to be a constructor, or like the cons, or a nil, or maybe it crashes when we look at it, or throws an exception, or runs forever. And only when we actually need the value will we look at it and evaluate it. And also note that the thunk is referring to the second element, or the tail of the original list, which makes sense. In order to know what's happening after the first element of the mapped list, we need to know what's happening after the first element of the original list. So let's look at the second element. We can do that using, for example, take 2 of L2 and then update. And we see that this has now progressed one step. So there's a capital N that came from the lowercase n, and we still have a thunk for the remainder. We can also try to evaluate the list a bit more carefully, and maybe only evaluate the spine of the list, but very carefully try to not look at the values. One way of doing that, I mean, there are many ways. Let's take L2, let's take it the first 4 elements of L2, and then let's map, I don't know, const unit over it, just so that we don't look at the values. So this gives us a list of 4 unit values, And if we now update, we see that something else has happened. Maybe I can make this a little bit larger here. So the tail of that list, after the first two elements, because we've evaluated up to 4 elements deep, we know that there's another const cell, and then, oh yeah, there's another const cell and yet another const cell. But the values at position 3 and 4, we haven't used them. And because Haskell is lazy, they are still Thunks at this point. And only when something uses them will they become a real value. So we can actually peek at position 0, 1, 2, 3, so 0 indexed, and update that. And now I predict that this thunk here will disappear and be replaced with a concrete value. And indeed, it becomes the capital O now. And the third value at index 2, that is still a thunk, because we haven't looked at it. So this is laziness in action. We also see that this thunk refers to the third element of the original list, and also to this function here, which is also referred to by this thunk that represents the remainder of the mapped list. Very likely this function here is the toUpper function. And if we evaluate this, it'll apply the toUpper function to the lowercase c and produce the uppercase c. We can actually evaluate things directly here in ghc-vis, so I don't have to worry about how I can evaluate certain things using the interpreter. I can just click here. So by clicking on this thunk, I'm doing the same thing as passing it to the seq function, seq, or pattern matching usually. And indeed, if I click that, I get the C. And now I could interactively here explore the rest of the program. So we get this thunk turns into a const cell. I can either evaluate the element, which should be a capital P now, or I can continue down the list. I can also just continue on the list and evaluate the spine of that function. And let me, so that now becomes a bit convoluted, mostly because they're all trying to point to this function here. I can also tell ghc-vis to hide that by hovering and pressing, click on that rectangle here, and then we get a more homogeneous view here. So I can choose to evaluate the thunks down the spine, or I can choose to evaluate some or all of the values in the list. And the Haskell program will not do more work than needed. That is the essence of laziness. Let's look at a different function. It's not too different from map, but it's still worth looking at. Let's look at zip-with. Let's zip with this, well, let's clear first. So we still have our list of L, and let's zip this with a list of numbers. So we can also, let's call it L2, and let's make sure that this is an integer. So this is we can look at the first 3 elements if you want. This is just the list of natural numbers starting with 1. And we can look at this in ghc-vis. And we see that, well, we've looked at the list up to the element 3, so this is not what you expect. It's a constructors with the elements 1, 2, and 3. And then there's a thunk that means that we haven't looked at this list any further. This list is infinite. If I were to print it now in ghc, I would just fill up my screen with many, many numbers, and it'll be evaluated as far as needed. So if I need the 4th element, then we see it has, the 4th element of L2, then we see that it evaluates further. So now let me create L3 as zip-with, and I somehow want to combine these two things here. So let's take the character and the number, and I don't know, let's multiply the number with data char, the ordinal value of the character. I pass L and L2 to it. So list 3 starts with 117, okay? And I can look at L3. Now we have this kind of big and noisy thing here. This is something called a BCO, a bytecode object. This is what ghci, the interpreter, compiles the expression that we write on the interpreter to. And there's something with numerics here, But this is all just distracting, so we can hover over this BCO object and press the hide button, and then things are nicer again. So what do we see here? We see that the zipped list, L3, well, it starts with 117, this is already evaluated. We don't know yet how it continues, but we do see that it is a thunk, so we can continue evaluating it. That refers to the second constructor of the first input list of L, and also the second constructor of the second input list, L2. It also refers to something called a PAP, that's a partial application. It's a function that is not fully applied. If I now look at the second element of L3 and update, then we see that this moves down. So now we have the 220 as the next element, and the thunk refers to the spines of the two input lists one level down. What happens if I do the thing where I only look at the spine here? So what we can do is we use this, actually just one good way of evaluating the spine is just using length on take 4 of 3, L3. Calculating the length means you have to go down the spine, but you don't have to look at the values. So this means we now have that our zip width list here refers to two more consoles. We've now evaluated them. Then it continues with the same thunk that we've seen before. But and maybe I can make this larger a little bit. But the values we haven't evaluated yet. So they are thunks. And we see quite naturally that they are now referring to this partial application, which is probably the function that we've written that combines C and N, and refers to the third element of the input list and also the third element of the other input list. And once we evaluate that, we'll get the result of that function. So one thing worth noting here is that L2 itself only has been evaluated up to the fifth element. Now we can continue evaluating L3, and the next step works fine. It refers to this console of L2. So let me evaluate that and also the element. What happens next is that in order to evaluate the sixth element of the output list, the zip width also needs the sixth element of the input list, of both. Now, okay, the first input list, the L, that's fully evaluated, so that's fine. For the second one, we don't even have the sixth element yet. That means in order to calculate the sixth element of L3, we also need to calculate the sixth element of L2, and therefore by forcing L3, we'll also force L2. So if we click on this thunk, we'll get the new element 6 here. And now this list has grown by one constructor. If we fully evaluate the zip width list, and let me just very quickly do that here, and then update, we will see that it is now completely independent of the other two lists, with the exception that they're sharing the null constructor. There's only one null in the whole Haskell program. And we also see that the L2, this infinite list of numbers, has been evaluated up to position 15. But not any further. So again, laziness means we're not evaluating these data structures further than needed. All right, so why did we look at zip width? Well, there's the very famous example for a recursive definition of the list of Fibonacci numbers. And we can now look what happens when we do the memory. So I can define the Fibonacci sequence as 0 followed by 1. And then the next element I want to compute as the addition of the previous two elements. That's how Fibonacci works. And I can do this by combining the fib list with itself. Namely, I want a zip width addition, the Fibonacci numbers, and the tail of the Fibonacci numbers. Notice that the Fibonacci numbers start with the 0th element of the list, and the tail starts with the first element, and this will result in the second element of the list. So second becomes the sum of the 0th and the first, and that sounds like Fibonacci. And indeed, if I look at the first elements of that list, that looks pretty promising. So how does this look in memory? Okay, we got a bunch of oh, I think, yeah, this might be, yeah, typical problem. We haven't specified the types. This means that this expression is actually polymorphic. And polymorphism, in this sense, here where it expects a type class constraint, actually means that really down in the machinery it's a function, which means we don't actually observe the effective evaluation because every time we will be calling it new. So let me fix that. We can fix that simply by giving this a type signature. And now it's really a value, not a function. I can look at the first three elements and I can view. And this now looks much nicer. So what we see here is that the Fibonacci list is a list. The first 1, 2, 3 elements are evaluated already, both the spine and the actual values, 0 and then 1 and 1. They're both pointing to the same one. And then we have a thunk, which means that this is where the next step would happen. And that thunk is referring to the one position earlier in the list and also a second position earlier in the list. And if I now evaluate that, we'll see that we get a new thunk for the continuation of the list, but also the value that we're trying to calculate is now a thunk that refers to the two previous values. It happens to be 1 in both cases, so that's not very nice. So let's go a little bit further. And now we have that after 0, 1, and 1, the next element is an application of this function, probably addition, I would hypothesize, to values 2 and 1, which would then give us next element in the list, namely 3. And of course, this is an infinite list. As long as we continue to evaluate the spine of that list, we will get always new list elements, and there will never be a null. This brings me to next topic, a small detour, namely the difference between infinite and cyclic data structures in Haskell. So let's leave Fibonacci behind and let's look at a simpler list. Namely the list of 1, and let's make sure this is an integer, 1, and so on. So it starts with 1, that's not surprising. And we can look at this in ghc-vis, and we see, okay, it is a console, first element is 1, and then a thunk. And if we look at the thunk, it'll create a new console. It still points to the same number, because we're not increasing the sequence, and we get a new thunk. And if we evaluate that, we get a new console, still pointing to the 1, and a new thunk. So this is an infinite list. All the elements are equal, it's always the 1, but as far as I evaluate that list, it'll fill up my memory with new concepts. Of course, there are many infinite lists where this is unavoidable. The Fibonacci sequence, for example, that is different values in every element, or simply the increasing number of natural numbers, 1, 2, 3, and so on. But for this one, it's a bit wasteful, isn't it? Because really, that list, the tail of that list, isn't really much different than the original list. It's just always ones. So we can actually define another list, L2, where I say, okay, it starts with the 1 as an integer. And then L2. So it refers to itself. It also begins with 1. And if I look at L2, I see that, and this is actually there's nothing to evaluate there, it's already done, there's no Thunks here, that it is a console that points to the 1 as the element, and then the tail of the list, the continuation, is itself. It's just pointing to itself. And this means I can look at L2 and I don't know, index it very deeply, and it'll not start evaluating things and filling up my memory, but it'll just run in cycles. It'll just follow the pointer to itself, in this case the list index function, and but it will not allocate something. And these kind of cyclic data structures are quite neat for certain applications. For example, what we can do, let's look at this example. Let's get the uncopyrightable list there again. And let's also create a list of, let's say the goal is to capitalize every second letter of that list. One idiomatic way in Haskell to do that might be to create, and I'll do it in separate steps, you would probably do it in one definition, the list of upper and lower function, or lower and upper maybe. So this is the list of data char to lower and data char to upper. It's a list of functions. And then let's look at this. Okay, so it's a list with two functions. We don't see which function is which one in this visualization, but we can guess one of them is to lower and one of them to upper. Now I can use the cycle command to, well, the cycle function to take that list and just keep repeating it forever. So let's define cyclic LU to be cycle of LU. And okay, we get some kind of bytecode object here. Let's look at the first element. So let's see how this evaluates in memory. The first element of that list, we've already looked at it by clicking on it, is the first element of the original list. And then there's a thunk that, among other things, refers to what happens in the original list after the first element. If we now look at the second element of this cyclic list, we get that it's the second element of the original list. We're just copying the elements, that's fine. And now what would be the third element, or the third spine element of that list? It is still a thunk, we haven't evaluated it yet, which points to the third spine element of the original list, which happens to be the empty list, at the end of the list. And it also kept track of the beginning of its own output. And what Cycle will now do when it reaches the end of the list is it'll just use the original, like its own output, as the continuation. So this pointer here for the third spine element will now just point to the beginning of the list. And now if you look at the CLY list here, we see it is a list containing of the two functions, and afterwards it just points to itself, so it's alternating between these two functions forever. And this allows us to very nicely zip this using function application with our original list L, and then we get, let's look at the first 4 elements of our very nicely alternating characters. So let's look at our lists that we have here. And this is getting slightly full, but I hope it can still make sense. So here we have our original list L. It goes uncopyrightable. Then here's the result list. And for the first 4 elements, it's already evaluated. So it's U, N, C, O with alternating lower and uppercase. Then we have this thunk. This is now the next element of the result list that we want to evaluate. If you click on that, we get a new console because the list continues. And 2 thunks, one for the element and one for the remaining list. The thunk for the element points to the function, and it's the first function in our original list. We can see that LU here in the first element points to the function. That is to lower. The thunk for the element of the result list also points to the points to the, this function. I think this is just the function application function, the $. Let me just hide this from view to make it get a slightly clearer visualization here. Okay, so this thunk now refers to the first element of the original list and the next element of our uncopyrightable string. And clearly, if we evaluate that, it'll apply to lower to P, which was lowercase, so it'll just stay there. Then the other thunk has now progressed in both lists 1 step down. So it refers to the next element of the spine of the original list and also the next element of the spine of the cyclic list here. And then if we do this one more step, we get a new thunk for the element. Now we're using the second function of the original list, which is also the second function of the cyclic list, apply to Y. This will produce a capital Y. And the remainder of that list is now a thunk, and because CLY, the cyclic list, is cyclic, it's now pointing to the beginning again. So while it traverses the original list step by step, it follows the cycle of the cyclic list to alternate between the two functions we want to apply. And we can do this all the way to the end to get that list, where every second element is still shared because two levels sharing this. This was a demonstration of the difference between infinite data structures that slowly fill up your memory and cyclic data structures like this list CLY that are semantically infinite, but they actually don't need more space in memory. The final thing I want to show you is how to use laziness, for example, for memoization. And actually we've seen it already. The definition of Fibonacci numbers in the way we did was memoizing the results, because in order to calculate fib of 12, we were using the already evaluated values of fib of 11 or fib of 10. What's more, if we were to, let me show that real quick. If I look at fib 10, let's maybe make 6 to be not so big, then this will also evaluate all the previous elements in that list, which meaning next time I look at fib of 4, there's no more computation happening. I just go down the list and look it up. And this is a common theme, and there's actually a very nice, slightly larger example for this pattern that I found in Stack Overflow, where Edward Kmet answered a question, how can we memorize a function like this? So this looks a little bit like fib, it's f and it's numeric and it has recursive calls, but the recursive calls actually, you don't need all the previous values. So here, for example, to calculate f12, we would only need f6 and f4 and f3 and 2 and 1 and 0, but not the values at position 7 or 8 or 9. And here the question was, how would we solve that? And then Edward Kmet has this very nice blog post or response here, where he explains how you can do it using memoization and laziness. So the first step is always to, or not always, the first step tends to be that you define your recursive function using open recursion. So instead of f just calling f directly, you pass a function to f, and then f will use that function for its own recursive calls. Now you can obtain the original function by then defining f to be f applied to what you're just defining. And there's a combinator for that called fix, so we can get that here. But we can also do memoization. And so the trick here is that you find a data structure that has a place for all the possible arguments to f. Now the arguments to f here are natural numbers, 0 and so on. And lists obviously have one position for each of these values. So by taking the list of all the indices, list of 0, 1, 2 and so on, and then mapping f over that list, we get the list of all the results of f. And then we can look in that list to get the result. And the trick is now that we define f, or we tell f that when it needs to look previous value, like do the recursion, then it should use this definition down here, which will then look up in the list. So for each element in the list, we're defining to be the result of f, but for all the recursive calls of f, we're looking up in the list. So let's look at that in memory. So let's clear this, and I've defined basically these functions in a file here, so we can load this in memo file. And I can, well, let's maybe look at the head of f list, it's 0. And now let's view f list. So let's see how this looks like. This is becoming very large. The reason is that, well, we've interpreted it and there's a bunch of stuff we don't really care about. this was less bad last time I tried it. I wonder if I need to maybe evaluate it a little bit more. Does it get better? Oh yeah, it's a little bit better. And there's a bunch of these BCOs, so let me just try to hide them. This is a bit, and with every one that I'm hiding, the display becomes smaller. Okay, this looks much better now. Okay, I'm back there. So what we see here is that we've evaluated the list for the first two elements, and we see that the next element of that list is unevaluated, is a thunk. There's a bunch of stuff that we want to look at closely here, but it's worth noting that if you follow this, or look into this structure of the thunk, there's a reference back to the original list. And that is because the function that we're defining, the faster f here, is of course referring to the f list. And let's see what happens when we evaluate, let's say, faster. Well, let's start with something simple. If we look at it at position 3 and update, we'll notice that we've evaluated more of the list. If we look at the position 8 and update, we'll see that we have evaluated more of the list up to position 8. For small numbers, the result of f happens to be the argument, so that's why we have an 8 here. Let's look at faster f of 12, because that's 13. That'll be easy to spot. And now we see that we have evaluated number 13. What we have not evaluated is other values that we didn't need. For example, the one at position 7 or 9 or 10 or 11. Actually, let me hide this thing to make the display a bit clearer. And we can see that the thunk at position 10, for example, still refers to the 10. That is because, well, the definition of faster of f list applied f to all the indices. So the thunk at position 10 is now this is a thunk that refers to the value 10. And if I evaluate that, that would be the same thing as faster f of 10. That should actually cause number 5 to evaluate here. And we see now the 5 is evaluated too. So this does the job. We've defined very systematically a memoized version of this function f by having a lazy data structure, in this case lists, that has positions for all the possible arguments for f, and then putting a thunk into these positions that would evaluate it once needed, and in that evaluation go through the data structure again to find the other values so that you're reusing any other work that has been done already. Now this data structure has a slight, or maybe more than slight disadvantage, that it's still this linked list. So if I want to do a f of 10,000, then for each recursive call that is happening during that evaluation, it still has to go through the whole list to find that position. Just that list indexing isn't very efficient. It's linear in time in the index, and we can do better. And Edward shows how to do better by defining a data structure that also has a position for each natural number, but where you can find that position more easily. So he does so by defining an infinite tree. So a value of this type is a tree. It has a value right there, but then there's also a left and a right tree where you can have further values. And because the tree is the only constructor of the data type, there's no leaf, this is really an infinite tree. It's going to be a tree constructor and then two subtrees, and either they are evaluated, so there's more tree constructors, or it's a thunk, but then there would be more if evaluation continues. And we'll probably never fully evaluate that tree. This tree data type, there's an obvious map function that allows us to map a function over all the values there. And there's a way of indexing into that tree that takes a tree and a natural number, and then if the number is 0, the value is right there. If it's odd, then we look in the left tree, and if it's even, we look in the right tree, and then so on. and this allows us to index into the tree. And just like before, we started with a list of natural numbers. Here we want to start with a tree, where in every element in the tree is the index of that tree. The construction isn't so important, so let's just look at that in memory. So, and because of how big it becomes when you use ghci, I'm actually going to use the compiled code to look at this. So let me quit ghci and restart with fobject code 02, which means when I know now load the memo module, it says compiling. It doesn't say interpreted here, which means it really was compiled, and we'll get slightly better view in the ghc-vis display. I still need to import ghc-vis. I'm going to start ghc-vis. I'm going to look at the nats data type. It's a thunk, we haven't looked at it at all. If I start evaluating it, we'll see that's a tree, there's a 0, and then we said on the left is odd number, so that's 1, and on the right is even number, so there's a 2. And then the 3 would be down here on the far left, and we can start evaluating this in order. Actually, it's not in order, the 4 was here and then the 5. Of course, we can also evaluate it using... Oh, we haven't looked at the indexing yet. Yes, we have looked at the indexing, sorry. So we can also index into that tree. So index takes the tree and a position, and maybe let's look at position 13. And we'll see that at position 13 is the number 13. That is very promising. It means that the index function and the nets function have the same idea about how the tree should be interpreted as a list of positions. And we also see that this has now grown the list towards the 13, but nothing else has grown. So we didn't need to evaluate all the positions up to 13, but only the part of the tree that leads to the 13. And now Edward defines a fastest f and a corresponding data structure, the f tree, pretty much the same way as previously with the lists. So we take the list, the tree of positions, we map f over that, and f was instructed to use this fastest f definition, which looks in this data structure. And if we now look at the f tree, well, it's a thunk. Maybe let's start by looking at the first element. Well, the first element of that tree, okay, it's still a thunk. Let me remove this sharing here. So the first element of that tree, that should be the result of f0. But we haven't looked at it yet. And indeed, it is a thunk that refers to the 0 that was in the original tree, in the tree of indices. So let's get this out of the way and look at something else. Well, now we have 0 in both cases. And then, of course, the thunks to the left and right of f tree, because it's just simply a map over the original tree, refers to the left and right subtree of the nets tree. And as you would expect, if I now index or use fastest f of 13, well, maybe that's a good example, but let's see what happens. We've evaluated more things. So in order to evaluate 13, you need the values, I guess, 6, so that is there, and then 4, and so on. And what I want to point out here is that we don't evaluate any numbers that we don't need. This is a bit hard to see now because it gets here this rather complicated data structure here. Let me clear and only look at the two trees separately. This will maybe make more sense. And let's hide this function here. Okay, so this is the f tree, and we've evaluated it to the position 13, and also the ones that we need to calculate 13. So the 6, the 5, the 4, the 3, the 2, and the 1 and the 0, but none of the other ones. And if we clear and look at the next tree, it has pretty much the same structure because we've evaluated the same positions in the tree. It's just that here we still have the indices. And as I now evaluate more of the original tree, so I evaluate more of the result tree. For example, let's go with, I don't know, 15. Oh, let's choose 24. Then the corresponding entries in the next tree are also evaluated. So we now have the 24. We also have the 12. And I think all the other ones are pretty much shared. So we can clear that and look at the tree of results and hide the common function thing here. And it's still the same tree. We got the 27 here. This was the result of applying f to 24. And yeah, the data structure only gets evaluated as far as needed to do the computations that we need for this memoized function. And because it's now a binary tree with a very nice structure, we can look up the values in logarithmic time, which makes this reasonably fast even for big numbers. With that, I'm at the end of my small lecture on heap data structures in Haskell, visualizing them with ghc-vis, sharing, laziness, infinite data structure, cyclic data structure, and how memoization brings this all together in a relatively practical application, if you know what you're doing. I hope you like this. If you have more suggestions what to do with ghc-vis, well, play around with it, try it yourself. If you have trouble installing it, let me know. Maybe open issue at the ghc-vis repository and tag me there, and I will see if I can help you. Otherwise, maybe send me a message on an email or Twitter if you want to see more of that. And enjoy all the other nice talks by Sarah. Thank you.